This begins our lesson 4.2 on quadratic relations. First thing we need to take is a note on quadratic relations. So you guys have a whole page there for notes. Maybe leave a gap underneath the diagram that I've given you, because we're going to be making notes around the diagram as well. So leave a bit of a space and then take this note on quadratic relations. It is a relationship between two variables in the form, a relationship between two variables in the form y equals ax squared plus bx plus c. Y equals ax squared plus bx plus c. Now in this case, we know a and b are called coefficients. They're the numerical part of these terms. Okay, so x is the variable and x squared. A is just representing the place of a number, which could be any integer or any real number, negative infinity all the way to positive infinity, could be anything. C, because it doesn't have a variable, is called the constant. That means no matter what happens to x, c will always be c. Right? This term won't change its value. If c is 7, then it will always be 7. It's the constant. Okay? This equation is only true and always true where a, b, and c are real numbers and a cannot equal 0. A cannot equal 0. What would happen in this scenario if a equaled 0? So if the a was 0, then this whole term would become 0. We would lose our x squared term, and we'd just be left with this linear expression, in which case we would not have a quadratic relation, we'd have a linear relation. So in a quadratic relation, we have an x squared term. B could be 0. We could leave the x term out, but the highest power of x in a quadratic relation is going to be x squared. The second thing we need to note about quadratic relations is the graph is a parabola. The graph of a quadratic relation is a parabola. A parabola which is which is U-shaped and symmetrical. It is U-shaped and symmetrical. In this point that it's symmetrical is going to be very important as we're doing applications of quadratic relations and the parabolas, the graph of a quadratic relation. So look at your diagram of a parabola. That is the graph of a quadratic relation, and we need to note some important points about it. Okay? The whole thing is called a parabola. So you should have an arrow pointing to the picture itself, and that is a parabola. So it is U-shaped and it is symmetrical. So what does it mean when it says it's symmetrical?
Even on both sides.
It's the same on both sides, right? If you flipped it over itself, it would line up right on top of itself. So we're going to go ahead and draw that line of symmetry. So every parabola will have an axis of symmetry. Axis of symmetry. And that's going to be important because if we were to move 2 units to the right of the axis of symmetry and 2 units to the left of the axis of symmetry, we would get the exact same y value for both of those places on the parabola. And that's an important point. You don't need to mark it yet. Another thing we need to note is that right here, where the axis of symmetry meets the parabola, anyone know what that point is called?
Intersection. Vertex.
That is the vertex of the parabola. The vertex of the parabola. And a few notes on vertex, which you can make probably just off to the right, or if you need more space, you can make them underneath all of the other notes that you have on quadratic relations already. But things we need to say about the vertex, 3 main points. It's where the parabola meets the axis of symmetry. So as you're writing them down, you should also be kind of rethinking them in your head to try and remember them, because these properties will come up again. Okay? We'll make a couple other notes on the vertex underneath. No, we'll make them right here. We'll see if they fit. The vertex is the maximum point if the parabola opens down. The vertex is the minimum point if the parabola opens up. So to draw those 2 quick examples for that, we could say this parabola opens down. That makes this the max. If the parabola opens up, that makes the vertex the min. Max and min. These are the key points about a parabola. Sometimes a parabola will also cross the x-axis. Sometimes a parabola will also cross the x-axis. So I believe you have an arrow pointing to this point and to this point. Do you have those? These are called the X-Intercepts. The X-Intercepts. Just like in a linear equation, except a linear system will only ever cross the x-axis once. A quadratic can cross it once, twice, or not at all, depending on where the quadratic is, depending on where the parabola is on the coordinate plane. Okay, there is your notes on the parabola, which is the graph of a quadratic relation. The last thing that we can also label is the Y-intercept. Y-intercept. In some forms of the equation, it's really easy to get the y-intercept. In some forms of the equation, it's really easy to get the vertex. And in another form of the equation, it's really easy to get the x-intercepts. So we're going to be learning about how to convert these equations once we learn more about them. Okay, everyone take a look at investigation A. We're going to compare relations of the form y equals ax squared plus bx plus c. So that is the standard form of a quadratic equation, a quadratic relation. And we're going to do that by completing the table of values for each relation. And then we're going to graph each of the relations that we calculate in a different color on the grid that you have below. So the first one there is the very basic, it's called the parent function for quadratic relations. It's the very first easy one. It's y equals x squared. Okay, so you have an xy chart table there, and we're going to use values of x from -3 to +3. from -3 to +3. So your X column should look like mine. Yeah, you don't have enough space, so you need to put the last 3 just underneath, which is fine. So this one's pretty straightforward. If we're finding that y is equal to x squared, then in this situation, on this first one, you can maybe make this note off to the left of your chart. Y equals -3 squared. All we're doing is subbing in, instead of x, wherever we see x, we're going to sub in a -3 and calculate what y is. Well, -3 squared is -3 times -3. +9. Okay? What about -2 squared? +4. -1 squared? +1. 0 squared? 0. 1 squared? 2 squared? 3 squared? Can you see a pattern in the y values? Yeah, they come down to a minimum at 0, 0, and on either side of that, they go back up, right? We'll be drawing that later. Okay, for y equals 2x squared, Tanner's going to take y equals 2x squared. Paul and Julia are both going to do y equals x squared plus 2x plus 3, and then compare your answers. Lindsay and Vlad are both going to do y equals -0.5x squared plus 3, so the last one. And Emma and Isaiah are both going to do y equals -x squared. Okay? With y equals -x squared, pay attention for a sec. Y equals -x squared. Okay? For that one, you need to keep the negative out front. So what you'd be doing there is going y equals -3 squared. So this -3 squared is +9, but you have a negative in front, so that's -9. Okay, so that negative out front just changes all the values, switches the sign on all of the values. Go ahead and do the one that you've been assigned, and then double check your answers with your partner, if you have one. And then we'll compile all our results. Okay, because this one looks a little bit tricky, in standard form we have x squared plus 2x plus 3. And we're going to see what that looks like when we sub in -3 for x. So over here in this column we would have y equals -3 squared plus 2 times -3 plus 3. And it's very important to use brackets in this situation so that you can see that the negative sign is permanently attached to the 3. Same here, it's 2 times -3. We don't want to mistake this with 2 -3 or anything like that. That negative sign belongs to the 3. It's the value of this whole number is -3. So -3 squared is 9. 2 times -3 is -6. And at the end we have our constant plus 3. This is 9 minus 6 plus 3. 9 minus 6 is 3, plus 3 is 6. So when x is -3, y is equal to 6. I'll go ahead and also do when x is -2, and then I'll leave you to do the rest. So again, we want to keep that negative sign attached to the 2 before we square it. Then we have 2 times -2. We're just subbing -2 in everywhere we see x in the original. And we have our constant of 3. -2 squared is +4. 2 times -2 is -4. And our constant of plus 3. Here we have 0 plus 3. That's our answer when x is -2, y is 3. Go ahead and complete that out for the rest of the chart. And then we can start to graph these relations. Okay, you can double check all the values for your chart up here, please. Double check all the values for your chart up here. Don't be confused. This is the last one. This pink one was supposed to be the last chart, but I ran out of space. So I moved it into the middle somewhere. And once you have all these, you should be able to identify in each of them the symmetrical nature of the y values. Can you see the symmetry that's in the y values? For instance, we can take this orange one. It goes from 18, 8, 2, 0, and then it starts climbing again, 2, 8, 18. And it climbs at the same rate as it decreased at the beginning. All centered around this vertex, which is 0, 0. Let's go ahead on our table. You're going to just plot these points, pick a bunch of different colors, plot the points, and then draw the smooth curve from each point. That's going to be the parabola for each of these separately, but on the same coordinate plane. Okay, if I can get your attention again, please. We're just going to, you can continue to quietly draw them, but we're going to discuss the similarities and differences. So think of something that all of the parabolas have in common. Think of some way that they are similar. And just put your thumb up on your desk or put your hand up to tell me if you want to share it. Okay, something that they have in common, something that's similar between all of the parabolas. Even if you were drawing, you still need to participate.
They all have a line.
Isaiah.
They're symmetrical.
They are all symmetrical. Thank you very much. Anything else? They are U-shaped. Excellent. Lindsay. They all cross the x-axis. In this case, they at least touch it, right? Or cross through it. Anything else? Paul?
Every single one of them have the same vertex, 0.
Do they all have the exact same vertex?
No. Oh, no, never mind.
There's one that has a different vertex, right? But mostly they all have a vertex at 0, 0. Now what's true is they all have an axis of symmetry of x equals 0, right? The y-axis is the axis of symmetry of all of these parabolas. So the parabolas have not moved left to right at all. They've only flipped upside down, and they have shifted up or down, which are the differences between them. Is there any other differences between the parabolas? Or are they?
Some are negative, some are positive.
Some are negative and some are positive. If it's negative, it opens down. So you can double check that. If the equation has a negative sign in front of the x squared term, the parabola will open down. If it does not have a negative sign and the x squared term is positive, then the parabola will open up. Anything else different about the parabolas? Maybe their shape or size, or are they all the same? Are all the parabolas the same shape and size?
No.
No. Some of them are stretched and some of them are squashed or compressed. So we're going to talk about vertical stretch and compression of parabolas as a way of changing their shape. But basically every parabola starts with the same shape. It's that y equals x squared shape, and then there are transformations done to it. So they change their shape by stretching, compressing, by moving up or down, or by moving left and right. And that's what we're going to be talking about more later on in this unit. The next thing we need to tackle is in Investigation B. Go ahead and look at Investigation B. That word finite differences, the term finite differences. And we're going to do the investigation before we explain what finite differences are. Have you ever heard that word before? Finite differences? Maybe, maybe not, but probably not. Okay, so complete the table for each linear relation, calculate the y values, then calculate the first difference by subtracting successive y values. We'll explain what that means as we get there. The first thing we need to do is fill in the y column of our table. So we've got y equals 2x minus 5. We've got an xy. This is called a t-chart with x and y. And the values of x that we have are negative 2, negative 1, 0, 1, and 2. All we need to do is sub negative 2 into the equation for x, and we will get the value of y. So here we go. We'll do it in our heads. If we put in negative 2 for x, then we have 2 times negative 2. What's 2 times negative 2? Negative 4 minus 5?
Negative 9.
Negative 9. Okay, let's put negative 1 in there. Negative 1 times 2 is? Negative 2 minus 5? Negative 7. 0 times 2 is?
0.
Leaving us with negative 5. 1 times 2 is? 2 minus 5. Negative 3. 2 times 2? 4 minus 5? Negative 1. Okay, so there's the y column of our t-chart. Now we need to learn what first differences are. first differences are the difference between successive y values. So here's all your y values, 1, 2, 3, 4, 5. Successive means they're right beside each other. They're right in a row. So the difference between these two y values is the first difference. We have -7 minus -9. That's how we find the difference between those y values. Well, -7 minus -9 is the same as -7 plus 9, which equals 2. Here again, now we need to take the finite difference between 5 and 7. -5 and -7. So we have -5 minus -7. That's the same as -5 plus 7, which is 2.
Can we just do
Here we have -3 minus -5. That's -3 plus 5, which is 2. And here we have -1 minus -3, which is also 2. What do you notice about the first differences in this case?
Should I already do that?
They're all the same. They are constant. They are constant. And look back at the equation. What type of equation was it? Is this linear or quadratic? It's linear. So in a linear system or a linear relation, the first differences are constant. So you have a question down there at the bottom. What is true about the first differences for a linear relation? The first differences for a linear relation are constant. First differences for a linear relation are We're going to leave the chart, the second chart on investigation B for you to do on your own. And if you flip the page, you'll see 2 more charts. Again, we are just going to do the top one. I'm going to leave the second one for you to do on your own so that you can confirm what we're discovering here. But again, we're going to now deal with quadratic relations. So you can see right away in that equation that we have y equals x squared minus 4. So here we're dealing with a quadratic relation. First step is to calculate the y values. Let's do it together very quickly. We sub in -2, we get -2 squared, which is positive 4. Subtract 4, 0. Put -1 in there. -1 squared is positive 1 minus 4, -3. Good job. Put 0 in there. 0 times 0 is 0. Take away 4, -4. Substitute 1 in there. We get 1 squared is minus 4, -3. 2 squared, 4 minus 4 is? Okay. Now again, we're going to calculate the first differences. Remember, the first differences are the difference between successive y values. So for our first one, we have -3 minus 0. Well, that's -3. For our next one, we have -4 minus -3. That's the same as -4 plus 3, which is -1. Oh, we're noticing that the first differences are not constant in the case of a quadratic. Then we have -3 minus -4. That's the same as -3 plus 4, which is 1. Then we have 0 minus -3. That's the same as 0 plus 3, which is just positive 3. So, if your first differences are not constant, you need to go for another round. You need to find the second differences. Okay? So in our second difference, we're comparing this first differences, the successive first differences. Okay? So now we're taking these values and we're saying, what's the difference between -1 and -3? The difference between -1 and -3 is -1 plus 3, positive 2. Then our next successive numbers, we're taking 1 minus negative 1. That's the same as 1 plus 1, which is 2. Then we have 3 take away 1, which is 2. What did you notice about the second differences? They are all 2, which means they are constant. Good. If you do the second chart on your own, you should be able to verify that the second differences in a quadratic relation are constant. So our question there is, what is true about the first differences, and then what is true about the second differences, okay? First, what is true about the first differences for a quadratic relation?
They're opposite.
Are they constant?
No.
No, they are not constant. The first differences for a quadratic relation are not constant. What is true about the second differences for a quadratic relation?
They are constant.
The second differences for a quadratic relation are constant. Then we have a statement there that says, therefore, da 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 da. What did we learn about first differences and second differences as a tool? Can we use them as a tool to determine whether an equation is linear or whether an equation is quadratic?
Yes.
What could we say? Try to develop your own rule and then we'll write something. Therefore, if the first differences of a relation are constant, it is a linear relation. If the second differences of a relation are constant, it is a quadratic relation. So this works both ways. If it's a linear relation, the first differences will be constant. If the first differences are constant, you know it's a linear relationship. That works both ways. Same with second differences and quadratic relations. Okay, one example to help us apply what we've learned about parabolas and quadratic relations. It is about Galleria Arches. So each arch in the BCE place Galleria, which is a big mall somewhere, can be approximated by the relation y equals negative 0.55 x squared plus 26. So this equation is approximately the same parabola as the arches in that mall, where y is the height in meters above the floor and x is the width in meters from the center of the hallway. So we have y is the height in meters and x is the width from the center of the hallway. So our parabola is going to look something like this, and our y-axis is going to go right down the middle there, and our x-axis is going to be like this. So in the positive x's, you're on the right of the center of the hallway, and in the negative x values, you're on the left of the center of the hallway, and the maximum height is here. The parabola is symmetrical on both sides. So that's kind of what we're looking at, okay? The first thing we're asked to do is to graph this quadratic relation. All right. So we've got some trusty graph paper out here. It's a little. Okay, in A, we are to graph the quadratic relation. So the first thing we are going to do, we're going to use the table of values to help us sketch a graph. Okay, so we have our equation here. It's y equals negative 0.55 x squared plus 26. And of course, we all have a calculator out. We're going to use the x values of negative 6, negative 4, negative 2, 0, 2, 4, and 6. So we're using a constant difference here between our x's. We're going up by 2's, all the way from negative 6 to positive 6. Now, if you have a calculator, you can do these fairly quickly and easily, but I'm just going to give you the answers. Essentially, what you would do in your calculator is you would go negative 6 squared, which you would just do in your head because that's 36. And then you do 36 times 0.55. You'd make sure your answer is negative, and then you'd add 26. Okay, so it's exponent first, then multiplication, then add the 26. The y column of your chart should look like this, 6.2. If you sub in negative 4, you'll get 17.2. If you sub in negative 2, you'll get 23.8. If you sub in 0, you'll get 26. Of course, that's our constant over here. If you sub in 2, you'll get 23.8, and we're starting to see the symmetrical nature of the parabola. If you put in 4, you'll get 17.2. If you put in 6, you'll get 6.2. Where x is the horizontal distance from the middle of the hallway, and the y value here is the maximum height, is the height with respect to x. So now we have enough information that we can plot some of our points. So you have a nice grid drawn there. You have an x-axis and a y-axis. Why don't I need to go below 0 in the y-axis?
Because there's no zero.
Yeah, we're not going into the basement of the mall, right? The mall just has an archway above the hallway. So let's plot some of our points here. We've got the point negative 6 and 6.2. Well, let's talk about our scale here. So I'm trying to go quick before the end of class. But our scale, the maximum height is right here, right? The maximum value is 26. So I maybe want to go up to about 30. And then for our x values, we're going all the way from negative 6 to positive 6. I've got 3, 4, 5, 1, 2, and then our negatives, we've got negative 3, negative 4, negative 5, negative 2, negative 1. So that's probably a good scale to use for our graph. And now you can go ahead and plot the points that you have. We have negative 6, 6. That's right up here. And on the other side, we also have 6, 6. So that's up there. Negative 4, 17. It's way up here. And we have positive 4, 17. That's over here. And then we have negative 2, 24-ish. Up there. And positive 2, 24. And 0, 26 as the vertex. And if you trace that curve nicely, you should get a somewhat, well, your parabola should be perfectly symmetrical. Mine isn't quite. But you should get what the archway looks like there. So we have a sketch of the graph. The next thing we need to do is describe the shape of the arch. Now the things we can say about it is that it's symmetrical. We can say that it opens down. It has a maximum at 0.26. The thing that our picture doesn't show is the actual shape of it, because our x scale is not the same as our y scale. So if all of these were 1-to-1, like if you had one box for every value of x and one box for every value of y, then because it's all measured in meters, you would actually have the shape, the exact shape of the arch. Ours is squashed quite a bit because I went up by 5s on the y column and by 1s on the x column. So ours is squished in comparison to what it should look like, but all of the data is still accurate if you're using the graph to calculate data.
Quick.
The last question that we have to answer here is how tall and wide is the arch? How tall and wide is the arch? How tall is the arch?
26 meters tall.
Because it's measured in meters, and we know the maximum point is 26, the arch is 26 meters tall. Okay? To find out how wide it is, we would actually need to find out the exact X-Intercepts. The exact X-Intercepts that's right here and right here. Now we have them because we could have put this into a calculator and we would have gotten that this X-Intercept is negative 6.9 and this X-Intercept, what does it have to be? If this one is negative 6.9 and it's symmetrical, then this one has to be 6.9, which tells us that the width of this arch is all the way from negative 6.9 to 6.9. So all we have to do is add, find the difference of what's in between here. So we go 6.9 minus negative 6.9, which is the same as 6.9 plus 6.9, which is 13.8 meters. So the width of the arch at the mall is 13.8 meters. The height is 26 meters. And that's how we use some of the information from our graph to answer application questions about parabolas. We can find the height, we can find the width, we have the axis of symmetry, and that's it for today. Make sure you do your homework. It's at the bottom of your worksheet page 242, section 1, number 1 and 2, section 2, 1 and 2, section 3, number 1. And please come prepared tomorrow to ask questions about those things.
Yeah.
Thank you.